and I had said that to solve this Poisson equation, the usual technique is you convert this W. So, you write this W as some psi plus a function. Okay, you write this W as psi plus some function where, so that del square W, which is the constant, you try to get this constant from this function. Okay. What happened? So, C1 x square plus C2 y square plus C3 x y plus C4 x plus C5 y plus C6, something like this, and this function has a constant Laplacian. Okay. So, we wanted to add this function here, and then we wanted to say that del square W is del square psi plus 2 times C1 plus C2. So, if we choose C1 plus C2 or 2 times C1 plus C2 such that it is 1 by mu dp dz, this is a choice that we make, then del square psi becomes 0. Okay, del square psi becomes 0. So, using this kind of technique you can solve this Poisson equation. Basically, we have changed the equation from an equation in W to equation in psi, and the equation is a simpler one, that is a Laplace equation. Okay. It changes the boundary conditions. Okay. It changes the boundary conditions because W is going to be 0 on the boundaries. So, psi is going to be minus of this function on boundaries. Okay. So, you have to choose a function which makes your life convenient and not more difficult. So, you have to choose a function such that for in this example we were writing that W, let us write it as psi and then plus half or some constant times, what were we writing, a square minus y square. Okay. Let us write it like this. So, in this case del square W is what, minus 2c. Okay. So, let this minus 2c be 1 by mu dp dz, in which case del square psi becomes 0, and the boundary conditions are that psi at x equals plus minus b for all y is what, psi at x equals plus minus b for all y. What are the boundary conditions in psi on these vertical walls? This is W, these are the boundary conditions in W. So, what is psi at x equals plus minus b for all y? Huh? So, what is it? Psi is what? Minus c a square minus y square, right? So, it is simply 1 by 2 mu dp dz a square minus y square. What about psi at x comma y equals plus minus a? What happens at y equals plus minus a to psi? It is 0. Okay. So, this gives us a chance to solve a modified system rather than solving this system of equations. This can also be solved, but we are choosing to solve this. Okay. It takes a bit more algebra to solve this Poisson equation. It is easier to solve a Laplacian equation. So, we can proceed with the standard separation of variables technique. Why can we do separation of variables? Why not doing any similarity variable or anything? Yes sir, Mr. Arctic Wolf. If you are not focusing, then you can leave if you have put your attendance. It is okay with me. I have anyways not really seen you in the class many times. So, जाओ जाओ, नहीं सॉरी क्या बोल रहा, कोई बात नहीं, जाओ, घूर क्या है यार जा ना, निकल, कोई बात नहीं, अटेंडेंस डाल ली तो चलो. Anyways, so this is what we start with. So, the equation del square psi becomes the equation becomes this. Okay. So, what we start doing is we say that this is equal to some minus k square and this is equal to some k square. I am not saying anything about k. Okay. I am not saying anything about k. K could be imaginary, complex, real, whatever. So, I am not really. So, when we write like this, some students think, oh, you are already assuming this is negative, that one is positive. Why? What if I do the opposite way? I am not assuming one is negative, one is positive. K need not be only real. Okay. We will get the values of k. Okay. The idea is we will get the values of k from our boundary conditions. So, what are the boundary conditions? So, first of all, what are the general solutions? General solutions are, let us say, a cos kx plus b sin kx, and then for y it is c e to the power ky plus d e to the power minus ky. Another way of writing this would be, so let us say these are c, so we can write them as c plus d over 2 cos hyperbolic ky plus c minus d over 2 sin hyperbolic ky. I hope you guys know these relations. This is how these are defined. Okay. So, this is how these are defined. Okay, so you can either write them like this, and you can write this new constant as some c tilde, you can write this new constant as some d tilde. So, I am going to write simply it is cos hyperbolic ky plus d sin hyperbolic ky. Okay. So, these are the general solutions of these two equations. The full solution is actually, so psi is going to be a summation over all possible values of k times these general solutions. Okay. So, this a cos kx plus b sin kx times c cos hyperbolic ky plus d sin hyperbolic ky. So, the full solution is a linear combination of all of these. Okay. So, you have to do a linear combination, and note that these a, b, c, d, they will be functions of k. Okay. They will be functions of k. There is also a possibility when this k is 0. Okay. There is also a possibility when the k is 0. So, in that case you will get linear solutions in x and y, and you can, excuse me, मैंने कितनी बार बोला तुम्हें वीडियो या फोटो मत खींचो, एक बार में समझ नहीं आती है क्या? तो मैं खींच लूँ तेरी फोटो, बता, डाल दूँ इंस्टाग्राम पे मीम बना के? दूर से अच्छे से दिखता नहीं तो पास आ जा भाई, कुर्सी खाली पड़ी है. 1000 बार बोला है तुम लोगों को फोटो मत खींचो, फोन मत लाओ, फोन तो ले आओ, चलो फोटो खींचने लग जाते हो यार, इतना आलस है तो फिर फोटो क्यों खींच रहा है? तो आजा, पास में आजा, कुर्सी खाली पड़ी है. दिमाग खराब करने से ना, मतलब कोई अपॉर्चुनिटी छोड़ते नहीं हो. So many times I have told you guys, don't click photos in the classroom. I'll put a camera, I'll click each of your photo, put up a meme with your face on it. Then you'll realize. Duds. So, this is your psi, linear combination of all of these, and the idea is that we want to find these a, b, c, d by using these boundary conditions. So, how many boundary conditions we have total? 4 boundary conditions, right? 2 in x, 2 in y, because this is a Laplacian equation in both x and y, right? So, how do we get the boundary condition? So, first thing is that psi at x equals plus minus b, or rather let us satisfy the easier ones first. Psi x y equals plus minus a is 0. Okay. So, if psi is like this, then you know that psi is an even function of y. Okay, psi is an even function of y. So, in these, what simplification can you make? If psi has to be an even function of y, so what can you say easily? Sine terms will have to be 0, and for them to be 0, basically dk's will be 0. Okay. No, I am saying it is an even function in y, not x. So, dk's are 0. Okay. So, essentially the solution variation in y is according to cos hyperbolic ky. Okay.
Sir, can we, if we put that in the psi expression, then sigma dk is 0, isn't it?
Yes, you are right. So, you get a sigma dk equals 0, but the idea is that we are trying to solve, technically you cannot solve for all dks. Okay, you have a single equation for all dks, but the idea is each solution which you are making up, if you make that satisfy the boundary condition, then the linear combination will satisfy the boundary condition. Okay. So, each term within the summation you are making that satisfy the boundary condition. Okay. Usually you have to do you have to satisfy the boundary condition for all of them combined. Okay. But of course, we cannot solve for, we do not even know how many valid values of k we have. So, then we will end up with an open system. You have infinite values of dk's, but you have, let us say 0 value, one equation or two equation, then you cannot solve anything, right. So, the idea is that we try to satisfy each each solution with the boundary condition in these kind of cases. Whenever there is no possibility of finding the constants by satisfying the whole boundary condition for the whole solution, then you go to the individual solutions and satisfy the boundary conditions. So, we get that all dk's are 0. So, C cos hyperbolic ky, basically that is the variation of the of your psi. Okay. So, essentially your psi will become something like, so I can absorb this constant Ck in Ak and Bk and simply write it as cos hyperbolic ky. Okay. This is what your solution is. There may be an arbitrary constant, by the way. Okay. I am not writing it anywhere, but I am expecting that that is implied. There is an arbitrary constant which might exist. Okay. And that arbitrary constant, since it is arbitrary, I am just taking it to be 0. Okay. So, psi has this kind of a variation in x and y. So, now we try to satisfy this boundary condition, that for all x, psi for all x, y equals plus minus a, which is a k cos k x plus b k sin k x times cos hyperbolic k a equals 0. Even if it was a constant, the idea is that this guy has to be 0. The only way this can be 0 for all k's is, so this has a variation in x, this is introducing a variation in x. The only way this can be 0 is, how can this be 0? AK and BK are 0. Then what do we end up with? That is a trivial solution. What else? What else can we do here? Cos hyperbolic Ka. When can cos hyperbolic Ka be 0? When can cos hyperbolic Ka be 0? Huh? So, again you guys are thinking about a real K. Do not think about a real K. Cos Ka, cos hyperbolic Ka can be 0 when K can be imaginary also. Okay. So, cos hyperbolic Ka to be 0, what does this mean? So, let us say K is some I lambda where lambda is real. So, this is cos hyperbolic I lambda a equals 0. What is cos hyperbolic lambda y? If you substitute k to be iota lambda, what do you get? You get a cos lambda y, right? So, this means cos lambda y or cos lambda a is 0, and now you have possible values of lambdas. What are the possible values of lambdas? What are the possible values of lambdas? Yeah. Where? Here? Huh? Uh-huh. Uh-huh.
Can't it be c times a square minus x square minus y square, because essentially del 2 w should be constant only, no?
Yeah, so I'm
So why have you taken this particular choice about c times a square minus y square?
oh, this one.
Yes.
So yeah, so you can write it as c a square minus y square. You can write it, you can do the whole derivation instead of taking like this. So you are saying, what do you want to write?
So c times a square minus x square minus y square.
Yeah, so you can start do this as well. Okay, you can do this as well. Your psi will change, but your w will remain same. The reason why I chose this is because this helps me satisfy, this helps me simplify boundary conditions. With this kind of a choice, you will not simplify any boundary conditions. Okay, you will have a, that's what I said. There is no particular choice, there is no reason or a thumb rule for a choice. It's always convenience. Okay, I'm also taking the path of least resistance here. I don't want to write a lot. Okay, so you can also do the whole derivation with c times b square minus x square. Okay, choosing a b square minus x square will simplify this boundary condition, have a function here. Okay, and you can proceed with the algebra just as is, there is no problem. So, having cos lambda a equals 0, what do you get? What is lambda a? 2n plus 1 pi by 2 for n equals 0, 1, 2. Technically, there is a plus minus also, right. So, this gives us possible values of lambda, okay, which are basically possible values of k. Okay, you have possible values of lambda or possible values of k. So, that means I can write my solution as sigma over n, and now I am going to change the subscript from k to n and write it like so a n. So, what does cos k x become if k is iota lambda? What would cos k x become? So, we know cos is simply this guy, right. So, cos k x will become cos hyperbolic lambda x and so on and so forth. So, you will get a cos hyperbolic lambda n x minus b n sin hyperbolic lambda n x times that cos hyperbolic becomes cos. So, you have a cos k lambda n y. So, this is what we have as simplified solution. So far we still have to find these a n and b n, and now we turn to boundary conditions in x. Okay. Again, boundary conditions in x are also symmetric. So, it has to be an even function of x as well. So, for it to be an even function in x, so psi for x has to be psi of minus x comma y. Okay. You can see the boundary conditions are symmetric. Just because boundary conditions are symmetric, it is not an even function. You can see the problem also physically. If this is your pipe, if I rotate the pipe by 180 degree, the flow should not change. Okay. So, for x, whatever the solution you have, you should have it for minus x. Okay. The flow is symmetric about this origin. So, if you look at your textbook Panton, there he does not solve for the whole system, he imposes symmetric boundary conditions at the center. Instead of writing this way boundary conditions, you can solve for the flow only in this region and extend the flow in these regions using symmetry. Okay. So, the symmetric boundary conditions are that derivative here and here will be 0. Okay. So, you can do the symmetric boundary condition way also, that is del psi by del x is 0 at x equal to 0 and del psi by del y is 0 at y equal to 0. That is also a possible way, you will get the same solution. So, we are saying that psi should be symmetric, which means b n's should be 0. So, the solution is a n cos lambda n x cos lambda n y. This should be cos hyperbolic, sorry. And now we just have to find these a n's. So, to find these a n's, we substitute the boundary condition, that psi at x equals plus minus b. So, x equals plus minus b for all y is n a n cos hyperbolic lambda n b cos lambda n y should be this 1 by 2 mu dp dz a square minus y square. How do we solve this? What do we have in front of us? What is this? How do we solve this equation? We have to solve for a n's. For every n, we have to solve for a n. How do we solve this? It is a Fourier series only with only cosine terms. Okay, this is a Fourier series with only cosine terms. We again use what we did in our impulsively moving plate with a bounded domain. We use the orthogonality. The same orthogonality holds for cos as well. Check this. So, let us look at this. Y goes from, what were the boundary conditions in y? Minus a to plus a, and we have values of lambda n, right? Yeah. So, what is this integral going to be? So, when n is equal to m, this is basically minus a to a half 1 plus cos 2 lambda n y dy. So, this is what? What does this integral become? This gives you dy minus a to a, this gives you 2a, and then you have this guy. So, you have a sine 2 lambda n y over 2 lambda n minus a to a. And what do we have here? Sine 2 lambda n y. What is sine 2 lambda n y, where lambda n is this, or sine 2 lambda n a? What is this value? What is this equal to? Sine 2 lambda n a. This is sine 2 lambda n a. Huh? Why? The integral or just sine 2 lambda n a? Why? Why this should be 0? So, it's some integral multiple of pi. So, both of these, at both of these it is 0, right. So, it is only equal to a. The integral is equal to a when lambda n and lambda m are same, but when lambda n and lambda m are not same, when they are not same, how can we write this? So, this is what you will have. So, again you are integrating cos of this. So, you will again have sine, of this, and then you will again say that lambda n and lambda m are not same, but their subtractions or additions will be some integer multiples of pi, you will get. Okay. So, this guy will also be 0. So, from here we obtain that this integral, this series can be solved when I multiply on both sides by cos lambda m y and integrate. That is the standard technique for solving coefficients of Fourier series. So, what we do is, so we have a n cos lambda cos hyperbolic lambda n b cos lambda n y equals 1 by 2 mu dp dz a square minus y square. I multiply on both the sides by cos lambda m y, integrate from minus a to a. So, the only term that survives is when n will be equal to m, rest all will be 0. So, on the left hand side we get a m cos hyperbolic lambda m b times an a small a equals 1 by 2 mu dp dz integral dy. Okay. You can solve this integral easily using integration by parts, and from there you can find a m's. Okay. After that your solution is complete. Okay. This is what the solution of your flow through a rectangular pipe is. Any questions? So, this method is very straightforward. Okay. All of this variable separation stuff that we did after converting the equation for w into equation for psi, you remember, you see that we obtained this. Okay. Now, as you will see that these kind of solutions, they do satisfy the Laplacian equation. Additionally, if I was to write, let us say something like this, Bn sine hyperbolic lambda n x sine lambda n y, if I was to write like something like this, then these also will satisfy your Laplacian equation. Forget about the boundary condition for now. Okay, forget about the boundary condition for now. These guys will also satisfy your Laplacian equation. Similarly, you can formulate any type of solutions based on the situation. Okay, you can cross multiply them, and I mean the lambda n's will be different. Okay, lambda n's will not be the same. They were same in this particular boundary condition case, but they can be different, and so you can have sine hyperbolic here. Okay, the reason why I am discussing this is because linear combinations of any type of these four functions combined in x and y, they can give you a very generalized solution of your Laplacian equation. Then you can filter out what will be the possibilities based on boundary conditions. Okay, you can just filter out the possibilities based on boundary conditions. And this method, when you write a solution knowing what are the possible solutions, this is called method of eigenfunction expansion. Now, I said some words here, eigenfunction expansion. What do we mean by eigenfunctions? You just know eigenvalues. What does it even mean by eigenfunction? So, the idea of eigenfunctions is something very similar to your basis vector. So, let us say I give you an algebraic equation for a vector in 3D and I ask you to solve it. You will immediately write, okay, vector is some x I cap plus y j cap plus z k cap, and try to solve for x, y, z separately. Eigenfunctions generalize this method for functions. Instead of vectors, they generalize it for functions, that any function which satisfies, let us say, a Laplacian equation, what you deduced is that it can be written as a linear combination of these functions, these functions in x and y. These are basis functions, these are called eigen functions. Basically it will be a linear combination, the solution will be a linear combination of these, and eventually your job is just to find the coefficients of these eigen functions. Just like you will find these coefficients of I cap, j cap, k cap, which are geometrically orthogonal to each other, here you have functions which will be orthogonal to each other, and you can solve for coefficients of those functions. Okay. So, it is a very similar idea as vector spaces in the functional space. So, a very engineering type of visualization you can make, that vectors are okay, finite dimensional vectors or finite dimensional tuples. Think of functions as infinite dimensional tuples or infinite dimensional vectors. Okay. And then all of those concepts of taking inner product and solving for the coefficients, they apply in functions also, as far as we are dealing with them. Okay. And that is what this method of eigenfunction expansion is. So, if you can find these eigenfunctions of different equations, for example, I can ask you, okay, what are the eigenfunctions of Laplacian equation in a cylindrical coordinate? Okay. You will see when you just go down, write it, and you will find that those are Bessel functions, let us say. Okay. You have a Bessel function if you have radial symmetry, if you have as axis symmetry and things like that. What are the eigenfunctions for Laplacian equation in spherical coordinates? You will determine those are Legendre functions or spherical harmonics as they are called. So, those are eigenfunctions, they are very characteristic to that particular equation. Okay. Knowing that a function solves that equation, you can immediately write it as a linear combination of these eigenfunctions. Okay. So, this actually gives us a chance to look at a very important concept, which is really not something particular to fluid mechanics, but I thought I will just go over it, and that is the concept of, so from Fourier series, how do we move to Fourier transforms? The reason why this is important here is because if you look at your solution, this is like a Fourier series. Okay, we eventually obtained a Fourier series and then we tried to find the coefficients of that Fourier series. When do we go from Fourier series to Fourier transforms? What is the essential condition when a Fourier transform is evaluated? Okay, what is an essential condition for expanding a function in Fourier series? Huh? It is a bounded function. Okay, it is defined on a bounded domain. Whenever you have a function that is defined on a bounded domain, let us say it is defined from, let us say, 0 to L, any function, then what you do is you repeat this function. Okay, you repeat this function and make a periodic function out of it, and then you express this using Fourier series by saying that capital L is the period of this new periodic function that you have extended. Okay. From Fourier series to Fourier transforms you go when you take limit L tends to infinity. Okay. When you take limit L tends to infinity, we go from Fourier series to Fourier transforms actually. Okay. And this need not start from 0 like this. Okay. You could have a function which is, let us say, like this also. Okay. So, it is really not dependent on if you are defining your function from 0 to some domain or minus L to L or something like that. Okay. So, it is really not dependent on that. So, have you guys covered Fourier transforms earlier? Then I will skip this part. Have you covered Fourier transforms anywhere? You don't know Fourier transforms? Signal processing course you guys have done, no? Electrical. Acha. It's a DE which you are doing now, signal processing. Okay. So you guys don't know what is a Fourier transform? Huh? Can we collectively just dismiss that? You don't know what a Fourier transform is? Yes or no? You can tell me. Fourier transform. Do you know what a Fourier transform is? No? Okay. So we'll just go over it. So the idea is that usually, how do we write a Fourier series? Let us say this is your function. You will say that okay, it is some expansion an cos knx plus bn sine knx. Okay, this is what your Fourier series looks like. You can change these to complex exponentials and eventually write that this is some cn e to the power I knx. Okay, you can write your Fourier series like this as well, that this is what your, and the summation is from let us say minus infinity to infinity. I am not defining what kn's might be, okay, I do not care what kn's are as of now. Okay. This is usually how a Fourier series is defined. When you define it for let us say a domain of size L, then these kn's have a specific form, and that is 2 n pi by L. Okay. So, this is how you can write a Fourier series. Now, once I write this as Fourier series, how do we determine these Cn's? How do we determine Cn's? So, we will again use the same concept. I will multiply it with a minus I km x, and I will integrate it over the whole x. X domain is let us say minus L by 2 to L by 2, and on the right hand side I will have okay. This is what we end up with. There is a very interesting property of Fourier transform which I want to get at, but so I wanted to show how we define Fourier transforms, and that important property we will use in some fluid mechanic problems only. So, it is not that I am doing this just for the heck of it, this is going somewhere. So, now what we say is, so this integral of minus L by 2 to L by 2 of e to the power I kn minus km x dx, what is this? What is this integral? Okay. This is what we have for this particular integral. Now, when we substitute it, we will get okay. So, from here again you can see, so this will become what? The top numerator, what does it become? What is the numerator become? 2I sine of kn minus km L by 2, right, divided by your I kn minus km. Okay. So, this expression we can evaluate when kn is not equal to km, and we can take a limit when kn is equal to km. So, when kn is not equal to km, what is kn minus km times pi by 2? Some integer times pi, right. When kn not equals km, then this guy is 0. Okay. Denominator is something finite and numerator is 0. So, this is 0. When kn equals km, then you can evaluate this in the limit kn goes to km of sine kn minus km L by 2 over Kn minus Km. There is a 2 here. So, you can multiply divide by L. Okay. So, what is this limit now? This is equal to L. Okay. So, when Kn is equal to Km, this integral is actually equal to L. When Kn is not equal to Km, this integral is 0. So, that means on that right hand side here, on this right hand side we only survive only one component, and that is Cm times L, and it is equal to minus L by 2 to L by 2 f of x e to the power minus I kmx dx. So, Cm is simply 1 by L. Okay. Now, this is Fourier series, this is standard Fourier series definition. The question is, how do we define a Fourier transform using this? How do we define a Fourier transform using this? You can think of it that in the limit L tends to infinity, what will happen? This guy is going to be get 0, but then this integral is happening over an infinite domain also. Okay. So, it's not necessary that when L tends to infinity you will just say, oh, this integral is going to 0, you do not know that. Okay. You do not know if this whole expression is going to be 0 in L, limit L tends to infinity. So, to define that, what we do is let, so we have to find in limit L tends to infinity, let minus L by 2 to L by 2 f of x e to the power minus I kmx dx be some h of km. So, I am defining this as a function h of km, okay. And then I will substitute that guy in this series. So, Cm is some h of km over L. So, fx is minus infinity to infinity summation h of km e to the power kn, sorry, e to the power I knx by L. This is what I have to evaluate in the limit L tends to infinity. Yes.
So how did you get Cm is equal to 1 by L? Wasn't it sigma Cn?
Yeah, but the same idea of orthogonality, that this integral is non-zero only when Kn is equal to Km. So, out of all the infinite possibilities, only when n is equal to m, this term, one term survives and rest all are all 0. Okay. So, that is why you are left with Cm times L.
So in the sigma you have only 1k, but in the integral you have
Huh?
kn and km.
Sigma I have what?
Sigma is only,
Over n,
is that n?
where here, yeah, this is n. So, I am just doing the bare minimum that is necessary to get to Fourier transform. If you are really interested in theory, you should look at the textbook, Kreyszig's textbook. There you will find all the theory very neatly defined. So, here what I am going to now write is, this is fx is this is n minus infinity to infinity, and I am going to write this 1 by L. So, this 1 by L I am going to write it as Km plus Km plus 1, let us write it like. So, Km plus 1 is 2 m plus 1 pi by L minus Km over 2 pi, okay, or a delta k over 2 pi. So, 1 by L is this delta k over 2 pi, and I can write this fx as minus infinity to infinity h of kn e to the power I knx and a delta k over 2 pi. Now, in the limit L tends to infinity, we know this is equivalent to saying limit delta k tends to 0. So, when I write this in limit delta k tends to 0, what does this get converted to? What is this? This summation is what? When I write it in limit L tends to infinity, we know limit delta k is going to be 0. So, f x if I write as n minus infinity to infinity delta k h of k n by 2 pi e to the power I k n x, and I write it in limit of delta k going to 0. What is this guy? Huh? How, that's how we convert integrals and summations, interchange them, right. So, if you have a function, then you will divide it using Riemann summation rule, and then you will write it like this. That is what we have. So, this is essentially minus infinity to infinity 1 by 2 pi h of k e to the power I k x dk. Where h of k is defined as, so this h of k I had defined. Now, in the limit L tends to infinity, your limits become minus infinity to infinity f of x e to the power minus I k x dx. Okay. And in the limit L tends to infinity, we have basically converted the summation of Fourier series into an integral, and this is called your Fourier transform. So, this h of k for this course, we will call this h of k as a Fourier transform of f x, okay, and this f x we will call as the inverse Fourier transform of h of k. Okay. This is your Fourier transform, this is inverse Fourier transform. Now, in some textbooks you will see this 2 pi that is appearing here, that will be interchanged, that is you will see f x is this guy without the 2 pi and h k is defined with 1 by 2 pi, it really makes no difference. These are pairs, these are pairs. If you can basically say, if you can basically say that f of f inverse gives you back the same thing h of k, or f inverse of f gives you back the same things, then really does not matter where the constant appears. Okay. And now, the interesting property that I want to use is, let us look at what is df by dx. So, if f x is defined like this, then what is df by dx? So, we have I of k h of k e to the power I k x dk. And if you look at this expression, you will see that I k times h of k is the Fourier transform of df by dx. Okay. Very similar to what you have in Laplace transform, where the Laplace transform of the derivative is simply s times that Laplace transform of the function, right. So, it is very similar to that. So, that means the Fourier transform of df over dx is essentially I of k h of k, or I of k times Fourier transform of f. Okay. And this property is, I mean, in fluid mechanics, in CFD, in signal processing, this kind of property is very useful. Okay. Throughout, be it experimental, theoretical or numerical fluid mechanics, this property is very useful. Okay. Why? Because let us say you want to solve an equation. So, there is a problem in your practice sheets where I am asking you to solve. Again, let us look at your heat equation, unsteady conduction or unsteady heat equation. Let us say you want to solve this, but this time your domain is not semi infinite, your domain is indeed infinite. So, let us say you have a y less than infinity greater than minus infinity, you have some initial condition, okay, you have some initial condition defined, okay, and it is really on an infinite domain, it is on an infinite domain, that is for y tends to infinity plus minus infinity, the velocity is actually 0. So, it really does not matter. So, the moment you have something like this, your u is defined over the whole y domain, then you can immediately resort to using Fourier transforms. And the good thing is, so let us say I define Fourier transform of u with a u hat, and I say that this guy is actually equal to simply minus infinity to infinity u of y comma t e to the power minus I k y d y. And instead of writing an equation in u, I try to write an equation in u hat. You will immediately see after substituting this, you will see that del u hat over del t, you will get minus nu k square u hat. Okay. So, the heat equation which was your PDE on an infinite domain, you have directly converted into an ODE. Okay, you have converted into an ODE, and what is the solution of this? Solution of this is u hat k comma t is simply u hat k comma 0 e to the power minus nu k square t. So, we have solved, instead of solving for u of y comma t, I have already solved for u hat k comma t. I have directly solved for the Fourier transform of the function. Instead of solving for the function, I have solved for Fourier transform of the function, and now using this inverse formula, I can find what is the function at y comma t. Okay. That is the power of this property of Fourier transform. Just by this property, we converted this second derivative into a simple algebraic expression. But notice that you can use this Fourier transform definition only when your domain is fully infinite, not even semi infinite, it has to be fully infinite. Okay. If you take a semi infinite domain, then you may have to do some tricks of extending the function for y less than 0 and then taking the Fourier transform and things like that. Okay. So, this property in our next lecture we will use, just give me 5 more minutes. So, we will use this property in determining the velocity induced by, so I am putting a quote on induced by vorticity. And the idea here is that if I give you a velocity field, you can immediately calculate vorticity field as del cross u. Okay. Given a velocity field, you can immediately calculate vorticity field. What about the reverse? If I give you a vorticity field, then can you tell me what your velocity field is going to be? Is it even possible? If yes, how? Okay. This is the question that we are going to use. It does not really look like a problem that we are trying to solve, but we will use the we will use Fourier transform, and actually there is a very nice closed form expression of velocity induced by vorticity. Okay. Knowing the vorticity, knowing the velocity, you can calculate vorticity, but what about the reverse? Okay. And to solve that equation, we will use all of this of Fourier transforms. Okay.